Hello Math 1224, this is Dr. P with the easiest way to prove divergence. Now I swear I'm going to try and make this video reasonably short. We'll see if I am successful, but I think I can make this one pretty short. So for the rest of this section, we're going to be mostly interested in deciding whether an infinite series is convergent or divergent. And recall that what those mean, convergent means the sequence of partial sums, converges to some finite real number, and divergent means that it doesn't. All right, and we're not going to be so interested anymore in showing what the actual specific sum of an infinite series is. Sometimes we can calculate those, but in most cases we're not going to be able to, and that's okay. We're just interested in whether they converge or diverge. Anyway, so take a look at this sum, the sum from n equals 1 to infinity of n over n plus 3. And let's just use this way of thinking about series to see if we can decide whether this series will converge or diverge. So let's do a little testing here. So if we were to write out the first few terms of this series, we would get, let's see, n equals 1 would give us 1/4, and then n equals 2 would give us 2/5, and then n equals 3 would give us 3/6, and then n equals 4 would give us 4/7, and then I'm just going to write out a few more. I'm not even going to bother simplifying the fractions that can be simplified. I recognize that there are a few of those. So let's just look at these partial sums here, or these terms, and compute a few partial sums, and just see what pops out of the woodwork here. So the partial sums are going to be, let's see, 1/4. That's the first partial sum, and then adding 2/5 is going to give me, let's see, I'm just going to do this mentally here. I think that's 13/20. And then adding 3/6 is going to give me, so the sum of the first three terms is going to be, I think, 23/20, because I know that 3/6 is 1/2. And then adding 4/7, the arithmetic's getting a little bit unwieldy here, but I think I'm going to get, let's see, 80 plus, let's see, 161. That's going to be like 241 over 140. Correct my arithmetic if you feel like it. And then, I don't know what that's going to give me, but let's step back here for a second and observe what's happening to the partial sums so far. So I want to look at these, and then let me create a new color here. There we go. Creating new colors on this thing is kind of a pain. All right. Anyway, so my first partial sum was 1/4, and then my next partial sum was 13/20, so that's a little bit greater than 1/2. And then 23/20 was a little bit greater than 1. And then 241 over 140, that's even bigger than, it's not bigger than 2, but it's certainly bigger than 3/2, because 210 over 140 would be 3/2. And then take a look at this. Just take a look at the next few terms of this series here. We've got 5/8, 6/9, 7/10. Each of those is greater than 1/2, right? And if I were to keep writing down further terms of the series, by the way, I should have written down that there's a ... here, meaning there are other terms after that are not accounted for here. But each of these terms is going to be greater than 1/2. And as I keep adding 1 to the numerator and the denominator, that's just going to increase the value of each fraction slightly. The fractions are never going to get bigger than 1, but they're also never going to get smaller than 1/2. So every time I add another term of the series, I'm going to get something that's greater than, the next increment of 1/2. So this will get me to something greater than 2. And then this will get me to something greater than 5/2, and this will, adding 7/10, will get me to something greater than 3. So the sequence of partial sums, is greater than the sequence, I'm just going to write this down and then explain it in a minute, 1/2 times n minus 1. So what I mean there is that the nth partial sum is greater than 1/2 of n minus 1. My reasoning there is my sixth partial sum, for example, is going to be bigger than 5/2. My seventh partial sum is greater than 6/2. My eighth partial sum would be greater than 7/2 if I were to compute it. And this sequence here goes to infinity. This sequence diverges to infinity. So looking at it in terms of these partial sums here, if I just think about partial sums of this series, I could ask myself, will there ever be a time when the partial sum is greater than, say, 1,000,000? And there absolutely would be. It would take about 2,000,000 terms, or maybe not quite so much, but I would get there by 2,000,000 terms or so. Will there be a time when the partial sum of this series is greater than 1,000,000,000? Well, sure there'd be. It might take about 2,000,000,000 terms, but I will get there eventually. There is no finite sum to which this converges. There's no finite limit to which the partial sums converge, and therefore this series here is divergent. It is both erudite and dauntless. Anyway, so that series there is going to diverge. And the main reason for it is because we just looked at the individual terms and saw that the individual terms, they're not getting smaller, they're actually getting bigger, and they're approaching some number that is not equal to 0. So what I'm saying there is that the terms of the series, so the individual terms of this series, n over n plus 3, converge to 1. Now, I'm not saying the series converges to 1. That's different. But the individual terms converge to 1. That's because the limit as n goes to infinity of n over n plus 3, that is equal to 1. So what that means is that as I, trundle along here and look at partial sums of this series, as time goes by, what's going on is I'm adding things that are getting closer and closer to 1. If I'm adding things to my partial sums that are getting closer and closer to 1, there's no way those partial sums are going to converge to a finite, bounded, real number. Those partial sums are going to keep getting bigger by about 1 each time. So what this leads to is there's a general idea here. The general idea is that, we know that the sum from n equals 1 to infinity, or n equals anything to infinity, really, of a sub n, this is guaranteed to diverge. Guaranteed to diverge if the limit as n goes to infinity of a sub n is not equal to 0, or if the limit fails to exist. In other words, if I want my series to have, an infinite series, to have any ghost of a chance at converging to a finite real number, I need for these terms here, the individual terms of the series, these must go to 0. Okay, so in other words, if I look at a series like the one I had in this example here, actually I've got it right here. That's beautiful. I don't have to go do my crazy zoom out like I usually do. If I look at the terms of a series and I can just spot those and say, oh, those don't even go to 0, they go to something else like 1, then I know immediately that the series diverges. I don't have to do anything else. That is sometimes called the divergence test for series. Divergence test. And it's called the divergence test because it is only good for telling you that a series diverges. It will not ever prove that a series converges. I cannot prove a series converges by showing that the terms of the series do go to 0. And I really can't emphasize this point enough. So just to give an example, one thing that we know from what we've done previously, so at some point we looked at this series, the series 1 over n, and we developed the p-series test, which says that this series diverges. The p-series test says this series diverges because p is equal to 1, which is less than or equal to 1. And under that condition, the series diverges. But you'll notice, let's see, let's choose a nice purple color for this. There we go. This is always the fun part, is picking the colors. But the series terms, they do go to 0. 1 over n does go to 0 as n goes to infinity. So all I'm saying is that the series terms going to 0 is no guarantor that the series will converge. It doesn't work that way. All I know is that if the series terms don't go to 0, the series is absolutely bound to diverge. And I'm going to stop right there because I'm under 10 minutes. And in the next video, we'll talk about a couple of other series tests. And then that'll be the last one before class. Thank you.